So we're doing solids, liquids, and gases. So states of matter. One of the things about these is that they're pure substances. We're not dealing with mixtures. So aqueous, I just mentioned that in the study set. So when we dissolve like salt in water, that's a mixture. So a solid, liquid, or gas, when we say something is a solid, liquid, or gas, there is only one compound present, or one of that present. So today we're going to talk about mostly liquids. Next week we talk about gases. Yeah, and solids come in a little bit here and there. So what's special about each one? Let's start. The picture here is actually wonderful. Pictures are worth 1,000 words, 1,000,000 words, really. A gas, the biggest thing about a gas is gases disperse. They are chaos. A lot of chemistry books actually start with gases. And I actually wanted to, but none of my colleagues, they all thought I was crazy. And that's because that's where a lot of chemistry started, was studying of gases. But it comes from the word chaos. And I guess if you could really say it with a good German accent, it does sound like, so that's what the word gas actually came from. And so they disperse. They have a lot of space. They take up space. So if in this room you open a bottle of perfume, when you smell something that's a gas, it's going to disperse and take up the whole room. If you break a liquid, it's just going to fall into a small pile. And that is what we're going to get into today. So we're going to put something here, is gases have weak attractions. They're really not attracted to each other. So whenever they come near another one, they just go in another direction. They really don't want to hang out. When we were in class, I used to say, you guys are like solids. I'm like the liquid. So I'm always moving around because I'll be at the board. I was commenting to my son, I feel like I've gained 10 pounds. And he said, well, that's because you used to get 3 hours every day of exercise. I probably walked 10 miles at the board. And so this being sitting in front of a computer is not good for my mermaid figure. So I would say the students were like solids. And that is that you're pretty much just sitting there still in your seat. You might have a little bit of wiggles or jiggles occasionally, but you're pretty much sitting there. And so they have a fixed shape and volume is often how they'll talk about it. They usually have, trying to think the word I usually use. I'm also fascinated because my brain thinks different writing on paper than when I'm at the board flowing. And actually the word flow, that is the key word. So gases disperse, they have weak attraction, liquids flow. Solids and liquids, I can't figure out how to find my person who just came back. Solids and liquids have strong attractions. And again, that's what the whole next page is about. So I'll call them strong attractive forces, and we'll get there, and this will make more sense then, whereas gases don't. And so that's why solids and liquids, the molecules are close together. Whereas in gases, they've dispersed. So I just realized what I wanted to say for a solid is solids have usually, almost always, a regular pattern. So they usually have some kind of regular pattern and they sit into it, and that makes them really nice. When we're talking about, I'm going to actually draw it down here. You guys can connect your dots if you get bored. And so if we're talking about, this is part of why dihydrogen monoxide, which is water, is so special, is water actually is very special because water ends up looking like this when we draw it out. And that's what our lecture on Wednesday is about, is how to draw the different molecules. I went with this lecture first on Monday. because the one on Wednesday will then go with the lab. And so with that, that gives you, yeah, also over time to work on that. Because of that, it looks, this is how we represent it, just doing it. That's what a water molecule looks like. So what happens when it's a liquid, it flows. Because of the shape, it has this very specific angle to it, it flows. As ice, as a solid, it actually makes these beautiful patterns. And it is one of the only solids that ends up with all this space in it. Most solids compact and fit really close, but that's one of the things that's special about dihydrogen monoxide is the solid has space in the pattern. And so the solid is less dense than the liquid. If you had any other liquid and you made an ice cube with it, and then you put it into it. So if you have a bottle of tequila, you can go and make an ice cube of the tequila and then put it in the tequila, it will sink. So alcohol is more dense when it makes a solid. If we had a block of lead and then we melted some lead and we put that block of lead in the liquid, the lead solid would sink. Whereas if you make an ice cube with water, you've all done it, the ice cube floats, and it has to do with this beautiful pattern it makes. So usually it packs tight. You can write that if you want, that usually it packs in tight and it is usually the densest, whereas H2O it's not. And so you all know that story. That's why the ice floats. And so water could exist below the ice in the oceans and stuff. Really the big key with liquids, the two big things, it flows. There is movement happening. So in a solid, they are fixed. They're kind of rigid. So that's why I'd be like you, where I can't see anybody, of course, but it's like the seaweed, it's in the water, right? You know, the seaweed is flowing. It's moving with the water. We have waves, we have all this movement. It is also why you can walk through water, right? You walk through the water. We don't walk on it. And as you're walking through the water, you feel the water because the liquid is flowing around you. There are molecules all around us in the air, but we don't feel the air. And that's because there's so much space between the particles that we don't have to push it apart to walk through it. And then of course, we can all walk on ice because it's a solid. And only if you're extremely special can you walk on water. All right. The other thing we need to talk about is changes in state. So when a solid becomes a liquid, we call that melting. Pretty sure you knew that. When a liquid becomes a gas, we usually say evaporate. You might see the word vaporize. So a vapor forms. And by the way, gas is when it's purely a gas. A vapor is when it was a liquid that became a gas. It's like a small distinguishing thing that is not a big deal, but it is technically what the term vapor means is when the liquid became a gas. So when you're heating a pot of water, you're creating water vapor. It's not considered, it is a gas particle, but that's why we don't call it water gas. We call it water vapor because it became a vapor from that. Or we might use the word boil. And you can go and Google and there'll be people who argue and say, no, these don't mean the same. For our purposes, they're interchangeable. Going in the other direction, which happens, probably will happen tonight because it's going to be pretty cold tonight. And so we'll see condensation happening. So the water vapor will condense. And so back when we'd be in class, you would all go out and your windows, you'd have to turn the heat on in your car to get your windows to clear off. And then this, of course, would be to freeze. Now, there is where you can skip the liquid. It's the perfect time, the perfect week to talk about this. This word is sublime or sublimation. So sublimation is dry ice is CO2. And so dry ice is called dry ice because it never becomes wet and never goes through the liquid. It actually, at normal room temperature and pressure, it just turns into the vapor. And so people will put it into water and they'll create the witch's brew and stuff, or make the smoke. You said be careful because it is CO2, so you don't want to be breathing it in. It's not going to kill you, it will just asphyxiate you because you're not breathing in oxygen. And so asphyxiation would kill you, but the CO2 itself is not. All right, there's something even cooler that's going on. That should go all the way to the solid. And that is, if you go the other way and you miss the liquid, that is not called freezing. That is called deposition or deposit. So we suddenly see a solid deposit from nothing, from the air. Another term for this, so deposition would be, and sublimation would be the full noun. That's snow. It's very rare to get it here in Gresham because we're pretty much at sea level. So anywhere where you're around sea level, it has to do with the pressure. So you go in Mount Hood, the pressure is lower, the atmospheric pressure, because of the elevation. And so you have to have the right pressure and the right temperature. And so it was wonderful because I went on a bike ride a couple of days ago and Mount Hood was pretty naked. It was pretty much all rock, just a little bit of snow at the top. And then this morning, when I went for a bike ride today, because it was a beautiful day, there was snow down lower and stuff. And so they had quite a bit of deposition happening. All right, and so it is when there's water vapor always in the air, and if the pressure is just right, it skips being a liquid. Here in Gresham, we get freezing rain because it becomes a liquid and then it freezes and everything turns into a sheet of ice. So these terms, they're here, we'll go through them. So therm has to do with heat. So exothermic means heat is exiting. And endothermic means heat into or absorbs. So when you're going this way from solid to liquid to gas, you are definitely absorbing heat. So you have to heat up the water on the stove to make it boil. So those would be endothermic directions. So that would mean the other direction is exothermic. They're fancy words. In my 200 level class, we spend actually quite a bit of time. Actually, we will run into them at the end of this term, the last week when we get into equilibrium, we'll run into exothermic and endothermic, but they're there in the notes, so I mentioned them. Something else dealing with heat that is really special about dihydrogen monoxide. Oh, we get to that on one of the next pages. I'll mention it when we get there. All right, so I redid the notes. And so I wanted to mention this term here to get us to the next page. When bonds form, we can have ionic bonds. So something I took from online. So an ionic bond is there's no sharing of electrons, the electron transferred, right? So the electron transferred from the metal to the non-metal. So we have a full positive and a full negative, or a full positive 2 and a full negative 2. And those are when we have a metal and a non-metal. And that's what last week was all about. Really, it was about ionic. Most of the compounds that you named were almost all ionic. There's a wee bit of covalent. This week, we're looking at the covalent ones. And so when you talk about covalent, you can share electrons equally, or kind of like a 2-year-old, right? You have your 2-year-old play with another 2-year-old. They don't really want to share their toys. They're really still at the age of 2, like an ionic. These toys are mine. Those are yours. Maybe it'd be more like a 4-year-old, or even us. You know, somebody says, you should really share that. And you don't really want to, we kind of do. So when we share equally, we call it nonpolar. It really has more to do with what polar means. Covalent, that is an unequal sharing, is saying that it is polar. And in my humble opinion, it's probably because I'm a biochemist, this is one of the two most important things we learn about this term, is this idea of polar and nonpolar. What the term polar means is there is a pool, right? So on the Earth, we have the poles, and so there's a magnetic pool. And really, this is magnetism going on here too. But this picture actually shows it really nicely. In a nonpolar, there's an equal distribution. So this is showing the electrons are being shared, and they're being shared equally. Everything's really nice. And most covalent bonds are this, that there's an unequal sharing. And so there is a pool. This cloud is showing that most of the electron is over here. So when you say, hey, you have to share that brownie, you should really share that brownie. And you're like, I really wanted that brownie. It looks so good. Somebody made it for me. And so you're like, okay, here's your piece, and I'll keep the big piece for myself. So we show these signs, and you'll see me doing this on the next page. And these are partial charges. So they don't have a charge. So I'll put that in quotes. It's like they have a partial charge, or they have an area of negativity and an area of positivity. In nonpolar, it's called nonpolar because there is no pooling. It's balanced. And so we're going to go through a bunch of examples on the next 3 pages. And unless there's a question, I'm going to move on. You guys can finish connecting your dots. Yeah. All right. Is there a question? All right. You should all make sure you're muted. Somebody in my other class wasn't, and then we got to hear a discussion going on in the background. All right, so solid, liquids, and gases. We're talking about liquids today. And you can think of solids too, but we usually look at it from the standpoint of the liquids. And it is more than just water, but again, that's why I dressed up like a mermaid. I put a little note on our thing, so a couple of people did. You can dress up on Wednesday as a fish, do like Tatum did and paint your face. That was pretty awesome. The shark was pretty scary. I'm seeing a theme, Tatum, with scary things going on.
I feel attacked.
So IMF, so you're going to see this abbreviation. Everyone just calls them IMF. Stands for intermolecular forces. The key here and why you should care is this is explains everything. This is one of the big things for those of you moving on to Chemistry 105 and 106 that we keep coming back to. And even if you're not taking any more chemistry because you're like, oh my gosh, this is enough for me. Really, biology is supposed to have a chemistry prereq because of this. And the word is inter, so it means it is a force. It is attraction between particles. And so I use the word particles, but molecules or ions or elements, basically between anything. Could be oranges. And attraction means that big word, electrostatic. Remember that word we keep running into? Means positive, negative. That's why I just went through the whole polar thing. My hope is by mentioning the polar tonight and doing this tonight, that when we do the Lewis structures, students do really great with the Lewis structures until we get to the polar part and they're like, I don't understand polar. So I'm hoping by doing it this way that maybe the polar will make more sense to more of you. But still do ask the questions. All right, these are attractions. These are not bonds. if we had a covalent bond on this, they would be off our page. They would be outside of my room. The strength of the covalent bond is beyond this attraction here. So these are attraction between different molecules. That's what's going on here. This is the attraction between. And if you notice, it's dots, dot, 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 dot. This is inside the molecule. That is a covalent bond. Again, we're going to be doing, that's what our whole theme this week is about. So this is a picture of the molecule, and then there's an attraction between the different molecules. So what we're talking about tonight is the attraction between the different molecules. All right. So this goes from strong to weak. Another place this shows up, so you think of DNA. So you've all heard of DNA. And so our DNA is two strands that make that beautiful double helix. What's holding the two strands together is these attractions. It's the H bond. It's just an attraction. It's like a zipper. If I had a jacket on, you can unzip it. But what's holding my arm, right, doing this to my shoulder, that can't come apart. My whole arm, that is, so each strand of the DNA is a covalently bonds to itself, and you can't break that. You can. That causes lots of damage. But we have a really easy way to pull the two strands apart. So the zipper, we can get out of our coat. You can put it back on, but it's really hard to break the sleeve off the coat. So covalent, again, is this pretty much permanent. It's like crazy glue. You have to get acetone and really work hard to get it apart. Whereas these, they're attracted. They want to stay together. They're like magnets, but we can pull them apart. And again, we show it as a positive negative. It is truly a magnetic attraction. Everything is truly magnetic. And it's pretty cool. That's where we're moving towards, is recognizing that. All right, the strongest is ionic. You guys already know about these. We talked about them all week, last week. So metal, non-metal. So these have a true positive negative. And that was those pictures on the previous page. That's why this is the strongest, because you fully transferred the electrons. Example is sodium chloride. All those examples, we saw so many on your homework in your lab. So you're great. You got this. All right. I'm going to skip. I'm going to write a note for H bond. There's space there. I'm going to come back to it. An H bond is an extreme dipole. So we're going to come back to it. So we're going to talk about dipole dipole. It is above the dipole dipole because it is stronger. It is just so important that it got its own category. But really, it is a subcategory of dipole dipole. It's just the strongest type of dipole dipole. So they call it dipole dipole because it has to be two molecules attracting to each other. And so it is polar attracted to another polar. So remember that term on the previous page. So when you see something polar, and we're going to do examples, and so you're going to see how to recognize these. And again, this is the attraction when I show dots. So I should have written that here. Attraction is dots. In a covalent bond, we use a line because they are sharing electrons. All right. So let's do this example. So the line means that's a covalent bond between the H and the Cl. This is why acids are special, but there's lots of other things that are polar. Acids are an extremely polar bond. They're not an H bond yet. We'll get to that. And so what happens is one of them is pulling the electrons more. Now looking at our periodic table, the one that's closer to noble gas wants the electron. The hydrogen wants to be a positive. It wants to give it up. It just hasn't yet until we put it into water. And so there's a pool. There's two ways you can show it. You can show that there's a pool of electrons that way with an arrow. And then we put a little positive at the other end of the arrow saying the electrons went the other way. Electrons are negative, so it gives the hydrogen part a positive area. It's not yet pulled apart. The other way to symbolize it is how all these little pictures are showing it, where you show a partial positive. So it's this funky D. It's a delta. It's a lowercase delta. And a partial negative. So again, it's an area of positivity and an area of negativity. It's not as strong as ionic, where it's fully transferred and you have a full charge. And so this would also have an area of positive and an area of negative. I mentioned both ways. I tend to, you usually see in here, because most of you are going towards biological medical sciences, and so in biology they tend to use the delta signs, and in biochemistry and in like my other class we tend to use the vectors because they're going more into engineering fields. All right, and so you get an attraction between this area of negativity and this area of positivity. And yeah, so an H bond is when this distribution is really big. We have a really big negative area and a really small positive area, or a big positive. So it's on the verge of becoming ionic. The H stands for hydrogen, so it is also known as a hydrogen bond, and it is not a bond. There is only one bond, and that is a covalent bond. When you are sharing electrons, that is not an attractive force. That is off this paper. That's outside my room. That's like in another state. There's no comparison. You have to have a chemical reaction or something really bad happen to break a covalent bond, like the chainsaw cutting off your arm. These are attractions. So find something it's more attracted to. And it says, bye, see you later. And nobody loses an arm. There's no blood spurting. All right. So unfortunately I called them ionic bonds and H bonds, hydrogen bonds, but they're not, they're attractions. H bonds happen, they're an extreme dipole. You have to have a hydrogen that is attached to either a nitrogen, an oxygen, or a fluorine. Only those three with a hydrogen can do an H bond. As we go through practice and the study set, this will become more solidified and liquefied, however you want to think about it. Why it gets a special category is because of the H and the O. Now, everyone online, if you go anywhere else, they're going to teach you this phone, F-O-N. I do it different because I don't know if you remember me talking about the gnome hat. I was looking at my gnome hats next door. I should draw a step as a gnome tonight. I have to do that next time. So I put a little G there, and that's a Knopf. So the hat that gnomes wear is actually called a Knopf, in case you never knew that. And so it makes it perfect to know. These three are really pulling the electrons. So they're right here, N, O, and F. They're pulling those electrons so much. And it's specifically when it's with hydrogen, because hydrogen is so tiny, it's the first one, that it makes it an extreme dipole. And where it really becomes special is in water. And there we go. We have an H attached to an oxygen. And what this picture is trying to show you, the oxygen will have the negative area and the hydrogen will have the positive area. And then if you have another water molecule, that's what that picture there is showing you, you will have an attraction. That is an H bond. So again, the attraction we show dots, and the covalent bonds we show lines. That's pretty important. All right. So the H bond is not between hydrogens. It has to be specifically a hydrogen attached to NO or F to another NO or F. So as we do practice, you will see this. All right, we got one more. And another picture over there. These have many names. And I'm going to go with, oh, by the way, London, sorry, I call them ionic H bond. This one I just call dipole. The full name is dipole dipole, but we can just say dipole once. I usually just call these London, but their full name is London dispersion forces. They were originally, because they were discovered at London College by Dr. van der Waal. So when I learned them in school, they were called van der Waal forces, and they've now changed the name about 20 years ago to induced dipole, because that's what they are. These happen in nonpolar and in atoms. So nonpolar, there's no pole. There's no area, positive and negative. How can there be an attraction if there's no pooling? So the easier way is to talk about it with an atom. Because in the very center of an atom are protons, and there are electrons orbiting. So what this picture is showing is the nucleus is where your positive is. And if the electrons happen to be for a moment, this is like a moment, you know, it takes you like a millisecond to snap your fingers. This is like a femtosecond. This is less than a femtosecond. This is like the attosecond. This is probably less than that. You get the electrons over here, and that will give you a negative. And then the nucleus is not quite in the middle. It's kind of like we all assume that electrons are moving in these perfect spheres. They're moving like waves, and you get this unequal movement sometimes. Waves aren't always perfectly moving, right? You've seen that at the ocean. You can't always predict them either. And so then if you have another atom, you'll get this where its electrons are over here, and you'll get this momentary attraction of the electrons from one atom to the nucleus of another one. This can happen between compounds. So again, we're talking intermolecular, between two different things. So it actually happens in all of these. However, if you don't have any of the others, this is all you're left with. So the question is usually going to ask you, oh, it doesn't ask you this way. I think it's in the study set or on the worksheet for Wednesday. Give the predominant intermolecular force. So the predominant is the most dominating. So whichever is the strongest, that accounts for like 99% of it. But they do all have London dispersion. Now, there is one more piece with London dispersion, because of course there has to be. Size matters for London dispersion, like they did with the alpha particles. This is not true for the other ones. So the other ones, it's the size of the charge that matters. So as you get a bigger charge or a bigger dipole, bigger pool, like fluorine's going to pool the most, because fluorine's like really close to becoming like a noble gas. So it's really desperate. It wants that last electron. Give it to me. So it's going to have the strongest pool. When you get to London dispersion, it's just happening and it's so momentary. But as you get larger surface area, you have more of this happening. The only time you look at this is if both of your choices are London. And again, you can call them dispersion forces. I'm going to call them London. So we're going to play the game. Just kind of go with it. You have your notes. So how do we recognize which one it is? If you have two of the same, so this is saying it's a sample with just bromine in it, and in another sample you have just fluorine. So it's not bromine and fluorine attracted to each other. It's just bromine here and just fluorine here. So which one's stronger? So these are both London. And the reason I know that they're both London is there's nothing to pull. So for a dipole, let's go back up and add notes. You need different elements, different different non-metals in the compound. Whereas London, there's going to be two key things. There's actually, it gets much deeper than this, but for our class, for London is if you have two of the same element. So these are called diatomics. We'll just write that fancy word underneath. We're going to see this word again during the term. O2 is an example of a diatomic. N2. So oxygen that's in the air, you've known since you were probably in kindergarten that everybody writes it as O2. Oxygen can't be by itself. So until it finds something else to react with, it will partner with another oxygen as O2. And so that's the same with bromine. It can never be alone as just Br. It's too reactive, right? This whole family, fluorine, chlorine, bromine, iodine, they're so reactive, they're so close to being there that until they find something else to react with, they always combine with another one of theirs. They're like Siamese twins. And so this is a covalent bond. These are considered molecular in nature. But there's no pool in there. So it's a bromine to a bromine. So that's a covalent bond, but you're with your identical Siamese twin, and so neither one's going to pool. So that is nonpolar. So if they're both nonpolar, they're both London. So NP is my abbreviation for nonpolar. I get tired of writing it out. Some students will just write non, but we're identifying intermolecular forces here. So if they're both London, then we look at size. So if they're both London, write notes. And so the one that's going to be greater is the bromine. How do I know that from what you would hope your teacher knows it? Periodic table has all the answers you need. Bromine, 79.9. Fluorine's just a svelte little 19. This is definitely much bigger, much larger. It's in the fifth shell, right? Oh, sorry, fourth. It's much larger. So only if they're both nonpolar, only if they're both London. All right, the next one, we have an H bond. And that is probably one of the big things from this lecture. If that's like the only thing that you can get on your homework, that's huge, is recognizing H bonds. This one is an H bond, the NH2. So how compounds are written, it's part of what this is. This one is polar. This means we have an H, we have a carbon, we have a nitrogen, the first one. So notice the H is not on the nitrogen. But something's definitely going to be pulling. The nitrogen is going to be pulling. So the closer they are to being like a noble gas, the more they're pulling. So we're getting a pull. So there's polar. They're not the same. Things are different here. So there's definitely pulling going on. But what this is saying is we have a carbon. So hydrogens are always on the outside. That's something we'll talk about more with Wednesday's lecture. So usually I have 3 hours tonight, and I had to make a choice of which one to do tonight. and we're going with it. All right. So the carbon, this is saying the carbon has, you don't have to be able to draw these. I'm just trying to illustrate what's going on, because for 5% of you, it makes more sense to see it like this. And for 95% of you, you're like, I'm okay with it like that. This is saying these H's are on this carbon. And that's what it looks like. The H's are around the carbon. And then there's the nitrogen. This is all hooked together. These are all lines. These are all covalent bonds. And then there's the nitrogen. And then we have some more hydrogens. So these hydrogens are on the nitrogen. That is what an H bond is when there is a hydrogen directly attached to either a nitrogen, an oxygen, or a fluorine, you have an H bond. And those are special. So my H bond wins. Now, I said explain briefly. This is really all I need. This is polar, this is H bond. Actually, I didn't want the word polar there. I wanted dipole. This drives a lot of students crazy. It's a silliness in the English language is what it is. I would take either word. The term dipole is a noun, and the term polar is an adjective. Since we're talking about intermolecular forces, that's why I was trying to give the name of the intermolecular force is a dipole dipole. But it's called that because it's polar. In this, the nitrogen's pooling. So there is a pull towards the nitrogen again. But there's also a pull this way. And there's all these pulls. So the pooling draws some students crazy, but the pooling's actually one of the most important things we do. All right. On the next one, you don't need to be able to draw it. It is polar. So the CH3Cl is polar. I see hydrogen, but I don't see NO or F, so I'm just going to call it a dipole. Now, looking at it, how do I know it's polar? How do I know there's a pool? Because with your periodic table,
The different nonmetals?
they are different. So if they're different, they're different because they're different. Somebody's pooling. It's the people with children usually do really good with this because they all are different. And so they pool different. So as soon as you see different things, there's a pool. This is ionic. How do I know it's ionic?
Metal and a non-metal?
Cesium, your periodic table always needs to be in front of you. We keep adding a lot. You know, it's something that Tiffany told me. She made a bunch of copies so she could keep adding stuff and writing things on it. But you want one that, yeah, and you don't have to know that it's cesium. We see the CS, and that's over here. And the Cl, there's not many non-metals. And so you start over this next week, actually with last week, when you did the naming, you should have become even more familiar with the periodic table. And so ionic, it's just our hierarchy. Ionic's at the top of our list. So ionic wins. I don't need you to say ionic wins, it's stronger because it's a full transfer. I mean, you can write that, but I'm just looking that you tell me this one's ionic, this one's dipole, so that's why that one wins. So I don't need a full sentence. All right, so the next one, this one is nonpolar. And back up here, I said there were two things that are nonpolar. They are London, but when you see two of the same element, like we did in our first example here, that is nonpolar. And the other thing, there are others, and we will fine tune this on Wednesday and next Monday, or I will avoid them because they're really not that important unless you're trying to develop something new. If you see only carbon and hydrogen, this is one of the other big things from tonight. That you recognize H bonds, because water does H bonds, and we are water-based. If you see only carbon and hydrogen, They do not pool on each other. When Linus Pauling developed his table of explaining all of this, it was based on this idea: why do carbon and hydrogens not mix with water? And so water, there's this big pool. And so carbon and hydrogen, he said, there must not be a pool. We can't go in there and see it. They can actually see the magnetic pooling, and then that the carbon and hydrogen, that there isn't. So if you see only carbon and hydrogens, like on this one and this one, just label it nonpolar, nonpolar. Now, this one, we see an oxygen. So it is polar. Now, we have two types of polar. We have dipole and we have H-bond. This is not an H-bond. So this is the hardest one for most students. The H's are written after the element they're attached to. So these H's are on that carbon, and these H's are on this carbon. So you don't have to draw it out like I was doing up here. You never have to draw it out. We will do that on Wednesday, but you don't have to. That oxygen doesn't have an H, so it is not an H bond. It is just the dipole versus London. I switch colors. Just writing in pink for that. Anyway, so which one wins? The dipole. So we'll circle the dipole. Dipole beats the London. All right, on the next one's interesting. They are both nonpolar because they are only carbons and hydrogens. So if I said, what's the intermolecular force, you would say London. So this is a tough one. You have a 50-50 chance, and when I ask this to the whole class, it's usually a 50-50 split. One of them always wins. So it's the one with the larger surface area. Only look at that if they're both nonpolar. They're both London. They're made up of only carbon and hydrogen. So the one with the larger surface area is going to win. All right, and that's the first one. So it might look, because I have this disproportionate large line because Bill Gates' program and me struggle with how to draw bonds, but really the CH3 should be snug up there. And so what the first one looks like is that, and the second one looks like this. This one has more surface area. That's, those of you take Chem 105, and even a little bit into 106. In 105, you get really good at just looking at molecules, and it's totally changes how you see the molecules, but it's organic chemistry, so it's all about carbons and hydrogens. All right, the next one, I see O's and H's. And you see H's or O's. So that OH, and there's an HO, and there's an OH. These both are H bond. So the first one's got an H bond because we have an H on an oxygen, and this one is 2 H bonds. So 2 is always better than 1. The more H bonds, the higher it is. So the double H bond does it. And our water molecule is ready to go to the next pages. Questions? All right. We're going to go through 6 properties of liquids and compare them. And I don't know why you should care. Some of this is pretty cool. Vapor pressure and boiling point go together. And so vapor pressure, a lot of these notes, once we get through this week and next week, they all come together. Last week, this week, and next week. Pressure is collisions of molecules. And a vapor is the gas above a liquid. That's why it's a liquid property. So it's a gas above a liquid colliding. So usually I have my tea in front of me, and so your tea or your coffee, there's always vapor coming off, and they're colliding with each other. They're creating vapor pressure. Now, if you have a closed container, so if you have a pot on the stove, this is why you have to go to school and get a PhD when you draw like I do. But if you have a lid on there, it's going to, and as you're heating it up with the fire, you're going to get more and more particles, and they start colliding and colliding more. So as you increase the temperature, that's what this graph is showing, and we'll go through it. As you increase the temperature, you're going to have an increased amount of gas escaping. And so that's going to increase your vapor pressure. So always, as you increase the temperature, and that's what part of this graph is showing, as the temperature increases, these lines all go up. Now, notice it's not a linear relationship. And then also, they're different. The graphs are not all the same. So, sorry, I'm trying to think where I'm going with this. We're relating it to intermolecular forces. So as you increase the IMF, you're going to decrease the gas escaping. And that is going to decrease the vapor pressure. So vapor pressure is all about the gas escaping. Yeah, being restricted to a small space really is amazing to me what happens in my brain. So vapor pressure is the gas escaping. Put a big star there. So as you're stronger and holding it into the liquid more, then less escapes and it's lower. So vapor pressure drops as the IMF goes up. So if we're comparing these, which has the higher vapor pressure, we want to go back to what we did on the previous page, figure out what type of intermolecular force, which one's stronger, and then we can answer it. So HF, C and HF, that is an H bond. Only thing that beats that is ionic, and I don't see ionic here. HBr, that is going to be polar. Again, there is a pull because they're different nonmetals. Everything's going to pull hydrogen except carbon. Carbon and hydrogen are best buddies. That's why we're carbon-hydrogen based. So HF is the higher IMF because it is the H bond. Making sure you have good notes. You do the homework. It's like every week, go through lecture, like, what did she just do? Oh my gosh, there's so much information. I keep looking at the cat clock. And then as you do the homework, hopefully it gives you practice, and hopefully you have your notes. You do your notes again. That's why hopefully I'm videotaping. So if this is a stronger IMF, the HBr has the higher vapor pressure. So the weaker one has the higher vapor pressure. The weaker one means more can escape. Vapor pressure is escaping. All right, this one we did earlier. They're both nonpolar. So if they're both nonpolar, the larger one has the higher IMF, the bromine, because it's larger. So they're both London. And so the winner is the fluorine. So the weaker, make a note to yourself, weaker IMF, higher vapor pressure. Or stronger IMF, lower vapor pressure. Whichever way makes more sense in your brain. All right, boiling point is always taught with vapor pressure, and that's what that curve has to do with it. So boiling point, you all know what it is. I'm gonna butcher the technical definition here, but we'll go for it. Boiling point is the temperature at which the gas escapes. The liquid turns to a gas. And it is when the vapor pressure equals the atmospheric pressure. So VP does not mean the vice president. VP means vapor pressure, and ATM means atmospheric pressure. You can write that underneath. So when the vapor pressure is the atmospheric pressure. So what this curve actually explains it. And I get to tell some fun stories here. So this is at different temperatures. This is the boiling point at different pressures. So this is showing when it boils. 760, and this gets driven home next week. 760, this says torr. And again, next week we do gas laws. It's just the order. Everything is in for a reason. Gas laws are, for the most part, the easiest part. And so, yeah. This is the same as 760 millimeters of mercury. I don't remember in the study set how I labeled the graphs. And this is the same as 1 ATM. That is 760 is a perfect day at sea level. So that is considered the normal boiling point. And so that's why it says normal. So if we look at water, its boiling point is considered 100 degrees Celsius. Here in Gresham, Oregon, or in Portland, or wherever you are, it's pretty much 100 degrees Celsius. If you're living up at government camp, it's probably more like 95 degrees Celsius. If you live in Salt Lake City, same thing. In Denver, that's why if you actually make brownies from a box, it has directions and it has a star and it says, unless you live above 5,000 feet, then you have to make your everything different. And so the Sherpas, so my last name, and nobody's asked me about it, but my last name, so Joey's dad is a Sherpa, climbed Mount Everest. So the Sherpas are these little people who climb Everest, and that's where they live. And they have huge lung capacity because they live at 10,000 to 15,000 feet. And so we cook very different in our house because he doesn't know how to cook at sea level. And so we have to use pressure cookers because where he lives, the water boils at 90 degrees. And so since you think that's great, the water boils faster, it's not getting hot enough to cook anything. So you can't actually cook rice. So they use pressure cookers. They're all over in the Himalayas, same with down in the Andes. They use pressure cookers. And so it builds up the pressure inside, and that tricks the inside of the pot to think the atmospheric pressure is higher. And so you can actually get the water higher. So when Sir Edmund Hillary and Tenzin Norgay climbed Mount Everest, if you're climbing Mount Everest, at the top of Mount Everest, you're at like 200, you're actually below 200 atmospheres. There's not enough oxygen molecules. You're at 1/4 the pressure. So there's not as many molecules. There's so much more space because what's causing the pressure is the collisions, right? So there's 25% as much molecules up there. When I was, like if I get above 14,000 feet, I can tell my body no longer can find enough oxygen. And so you're at about half the pressure. So Mount Rainier is at about half the pressure. And the water's boiling, I think at like 85 degrees. So when you're on top of Mount Everest, when they get into the death zone, their water is boiling at like 65 degrees. You can't cook ramen noodles. So everything comes out raw. You can boil water, but it's not very hot. And so you can't actually boil an egg on top of Mount Everest. So the temperature of the water has to be above 65 degrees to denature, to jiggle apart the proteins. And so this is just showing that as the atmospheric pressure changes, the temperature increases. And these are just different substances. And so boiling point is the temperature the liquid escapes. Going back to our IMFs, as you increase the strength of the IMF, you're going to need higher and higher temperature. So temperature is a measurement of jiggles. It really is. So it's how much jiggles you have going on. It's kinetic energy is the technical term for it. So if you want, don't like the giggles and jiggles, but the jiggles, ever since I started doing that, and usually when I'm teaching this in class, there'll be a couple students who just sit there and start jiggling. There's jiggle machines, and they help you to burn calories. So you're all in a dark box, so I can't tell if anybody's jiggling. But as you're jiggling and jiggling and jiggling more, you get to a higher and higher temperature. So stronger IMFs need more jiggles and giggles to escape. So they need a higher temperature. So they're going to have a higher boiling point. So they need more jiggles to break that attraction and more giggles to break the attraction. So to escape out into their own, there we go, and wiggles. So it's the opposite of vapor pressure. In this curve, actually ethylene glycol, there's a question in the homework where you look at the curve, and actually we're going to do that down here. So let's answer this first question, which is the higher boiling point. The rest of this goes pretty fast, these first two, because the pattern you start seeing, the HF, because it was the H bond. This is the same question we just did. And then the next one, the bromine. So they were both London, but it has the higher, greater size, so greater IMF. So when you're looking at vapor pressure, we went with the weaker one. With boiling point, we're going with the stronger one. So higher IMF meaning stronger. All right, so we're going to look at that curve at the top of the page. And all right, now I can see it. The highest normal boiling point between these three, I threw out this guy down here because a lot of people didn't see him, is the water. The water has the highest normal boiling point. So this graph was really nice. It showed us, it actually wrote in the boiling points of each of these substances. We don't actually even need to see what they look like. From this property, we can answer all these other things. So if that has the highest boiling point, then that would mean the water, H2O. I think if I write as H2O, that's not making a huge leap for anyone. H2O is water. All right, you know what, C, let's just throw out C. I don't know what I was going for there. Get rid of that question. It's really bizarre. All right, D. Let's say we go to 450 Tor, which is Mount Rainier. So we find around 450 and we come across until we get to the water. And yeah, I was around approximately, right? So we get about 85 degrees. So it's where you hit the curve. The curve is called a vapor pressure curve, but the curve is telling you the boiling point at different atmospheric pressures. So as you climb, yeah, and actually when our weather changes, the boiling point will be different. And some people can actually feel changes. They'll say, my bones hurt. I know it's going to be colder. So when this cold front came in, I think the pressure actually increased. All right. But I always get it backwards. It might have been that it drops. I'm not going to ask you that question. All right. So at 250 Tor. Now, comment I always make to class. You are probably never, ever going to read a vapor pressure curve in your life again after this class. However, you're all going to have to read a graph of some type. And so see that is what's going on. That, okay, it's just showing that I know how to read a graph. So if we're at 250 Tor, which is top of Mount Everest, apparently. I thought it was closer to 200. Yeah, my line's not going to be great. So we're getting around like 70, I don't know, 73. I think my number's off here. Because I think it should be, can we change that to 200? Just change it, it's 200. All right, so then you would just come around, and it's 65. I can do that because I'm in complete control. You're all muted. You can moan. I don't even know if you're even there. All right. So F and G go together. So we're going to find this point on the graph. It's the same question, but just looking one at the ether and one at the ethanol. So 40 degrees and 400 torr would be this point right here where my star is. So I put a star there. And if we look at the diethyl ether, the ether is already a gas. Sorry, this overhead and nighttime, it changes focus. This curve is where the liquid turns into a gas. So at each point in this curve, it's changing from a liquid to a gas. So the ether has already made that jump at this temperature. So it is already a gas. The ethanol has not yet made its jump. It's a liquid until we get to here, and then it becomes a gas. And so it's still a liquid, as would be the water and ethylene glycol. All right, in this interest of time, we're going to move on. The next one is called, has a fancy word. It's a wonderful word, enthalpy. Enthalpy means heat. It is a Greek word for heat. The symbol is triangle H and then subscript VAP. The H stands for heat, and the triangle stands for change. So I've read some really great explanations of the difference between temperature and heat, and they're brilliant. And I read them and I go, oh, I get it. And then this brain never remembers it as beautifully as online. So if you want to read exactly what the difference between heat and temperature is, the units are different, but they still have to do with jiggles and giggles. As you add heat, you get more jiggles. So the enthalpy of vaporization is how much heat to change from a liquid to a gas, as opposed to this one that was measuring the temperature at which that happens. This is measuring the heat. Just a comment for you about heat. Heat is measured in calories. It's also measured in joules, but food calories. So when you eat, you get a lot of heat, you get a lot of energy. So heat is a form of energy. Temperature is not. So children, when they eat candy and the quick calories of junk food, all the processed food and fast food, they get really hyper and stuff because they get this over explosion of heat and energy in their body, and then they crash because our body doesn't know what to do with them. All right. So again, the rule is, since we're looking at jiggles to escape, higher, stronger IMF is going to be a higher delta H of vaporization. So again, the HF and the bromine. So you need more heat, you need more jiggles. They're really looking at the same thing, just from a slightly different angle. So boiling point and delta H of VAP, it's just another term. And if you keep in mind the H just means heat, or the word enthalpy means heat. There is a question I have here that I do want to mention, and it is, why is the delta in this curve? We're not going to actually do anything with this curve. Why is this? This is number 4 is the delta H of VAP. And I'm sorry, yes. And number 2 is the delta H of fusion. And what's happening at 1 is you're a solid. What's happening at 3 is you're a liquid. What's happening at 5 is you're a gas. So this is saying, this is not correctly labeled. That should say, instead of time, this should say heat. So as you add heat over time, I think is what they were saying, you have a solid, you have a piece of ice and you add heat until it gets to 0 degrees Celsius. So this is specifically water they're doing here. And then it goes through a time when it's both a solid and a liquid. So you've all done this at home where you put ice in your drink, whatever it is, right? Your lemonade or your iced tea or your water. and you have both the liquid and the solid together at the same time. And so you're in this area, you're actually at 0 degrees. As long as there's ice present, it should be at 0. Until you hit a point where all of the solid melts, you've added enough heat, and now it's a liquid. And as you add more heat, the liquid is going to increase in temperature until it hits its boiling point. And then you've all done this. The pot of water keeps boiling until it all boils off, and now it's all in the gas phase. The heat of vaporization is higher because the big difference, this is back to the very first page, the big difference between a gas and a solid and a liquid. Gases have weak attractions, or IMFs. We can add that word now. Gases don't have that attraction for each other. And that is because they have so much chaos. They're all about jiggles and wiggles, and they're wiggling and jiggling enough. They don't have time to hold hands or be attracted to anything. They're just like too much wiggling and jiggling, which is a good thing. All right, here's the liquid. There are attractions, but they're flowing past each other. They're attracted so they can keep moving. They're not stuck. And then a solid, they get to a point where they're kind of sitting there because they're usually at a very cold temperatures. They just don't have enough oomph to get moving and stuff. So that kind of relates everything we've done for the past hour. All right, we're gonna cruise through this last page because we have gone through the intermolecular forces. Surface tension is when you have a liquid. So this is like my liquid here. It's the molecules at the surface have an attraction for each other. So it's the attraction that was I usually draw big elaborate pictures on the board. Attraction of the surface molecules for other molecules. To the other molecules. So that's what I was trying to draw here. So we have, notice I'm doing dots. So that's why the bugs, water, because of the H bonds, has a really high surface tension. And so that's why those water bugs can walk on water. You're going to get, I think, I can answer this better on Wednesday. So this is something, I don't know if Kaylee, if you did this with me, if we did the square bubble ever when you were in my class, but bubbles are always spheres because of surface tension. So you can get those wands that are shaped like the heart or all these different elaborate shapes, and you blow the bubble and it always comes out round. And so I did a whole talk on it, and it turns out there is a way to make a square bubble. And that's all at school. And it's also why it's actually one of my very first kids class. I was like, oh my gosh, it was Sunday night. The class was on Monday. I'm like, I don't know what I'm going to do. And one of my students said, we had a study group. He said, well, there's something about how you can get like 100 drops of water on a penny. Like, what are you talking about? And so we all got out pennies and droppers, and sure enough, if you're really patient. And so I did that with the kids for an hour, and they were so into it because you have to, and they sat still. And so it's a challenge I'm going to have for you all, is how many drops of water you can fit on a penny. And it has to do with surface tension. Water, because of the H bonds, there's this huge attraction, and so you get this huge bubble on the penny. So higher IMF, higher surface tension. Real quick comment, surface tension and surface area are not the same thing. So surface tension is this layer on top of the surface of anything. Higher IMF, higher surface tension, because there's more attraction. So the HF and the bromine, these were all the same question, just with a different thing. All right, viscosity. And so this will show up next week. We'll talk about it more with your lab or a bonus who can get the most on there. You have to like, yeah. This is actually very cool. So viscosity, they give this the definition is resistance to flow. It is, it's stickiness is one of the way. And so again, the technical, I'm trying to remember the word I usually use. The technical definition you always find is resistance to flow. So an example of something that's viscous would be honey, real honey. And so real honey is really viscous. It's sticking together. And I actually have lava lamp that I usually have going on during this lecture. And so that works with actually a change in density with the temperature, but also viscosity. This is actually a real thing. So pitch is the tar we use on our roads for tarring the roads. It is the most viscous substance. 1 drop falls every 8 years. So this little funnel is filled with pitch. And it may have been 8 years ago. I'd have to really think about this. I think it's 7 years ago, 6.5 years ago, the last drop fell. So it's actually in a museum in New Zealand, and they have a camera on it, and they actually switched over people's like video game channels and stuff to watch, because you can see it, it's hanging like this for years, for like 4 years, until the drop finally falls. So obviously, if you have greater attraction, you are more viscous. So our answers on that would be the HF and the bromine. So last one, volatility. We're almost there. I am going to do the last page. I'm going to make it a separate thing so you can sign off when I get there, but let's finish this. Volatility is ease of evaporating. It is actually a chemistry term, and it was made into a term also for people who are quick to anger. So if we're going to ask which state of matter is the most volatile, has the most anger, has the most chaos, it would be a gas, because they're moving around, they're chaotic. That's what happens when people are angry. They just start, their hands are flying, and their face does weird shapes and stuff. So ease to evaporate, oh, we're back to this. The higher IMF is going to be the lower volatility. These guys don't want to evaporate. They're happy to be attracted to each other. So the weak ones are volatile. So that's the other way to say it. Weak attraction, weak IMF are the most volatile. So we suddenly have the other answers. So there is a reason these 2 pages were in the order. The very first one, vapor pressure, and the very last one, volatility, were the ones that were in opposite attraction. So the weaker ones were the most volatile. So the answers for this, just so you have them, and again, the homework will have you going, hopefully you took decent notes, and walking through this, and we'll walk through the homework. And so these are both only carbon and hydrogen. That means they are
Covalent.
They are nonpolar. They are a covalent bond, but we've now taken it one step past that. If it's only carbon and hydrogen, they're nonpolar. There's no pole in that covalent bond. So absolutely, you're right, Tiffany. But it is that they're not pooling. So you look at size. This is the stronger IMF, is the C10. So for viscosity, the C10H22 is going to win. For volatility, we want the weaker, which is the smaller, the C6H12. Just we have your notes, you can go back and look at it. So for viscosity, we want the stronger one, which is the this one. They're both nonpolar. This one is greater surface area. All right, on the next one, does anybody see it? Tiffany, you're not allowed to talk anymore. You don't have a voice. See the OH? See an OH? Let's go H bond. This one, this is the monkey in the middle. Oxygen's in the middle. These H's again are on the carbon. So this is polar or a dipole. But these H's are on the carbon. These H's are on the carbon. So the H bond is stronger. H bond is just an extreme. So greater surface tension is the stronger one. So the H bond, we'll just write H bond. And it also wins, the heat of vaporization is also the H bond. So the stronger one wins both of those. All right, the next one. Carbon hydrogen, nonpolar, London. And the other one, we have different stuff. So something's pooling. So this is polar or dipole. So again, dipole is and London are the names of the intermolecular force. So in the homework, I ask what's the intermolecular force, but it comes from this category of polar and nonpolar. I know there's a question in the homework, and I even said in it, did she talk about this? And I specifically had it in there because I knew time would become, and that happens every year. All right, vapor pressure, the higher vapor pressure is the weaker one, which is the London, the CH4. The higher boiling point is the stronger one, which is the CHCl3. So, questions? All right. So it is a couple minutes after 8. If you want to leave, you can. I was going to go through practice naming, or I can save it. Yeah, Wednesday's going to be busy. What do you guys want to do?
I'll stay to practice because I won't be able to be as here on Wednesday.
Do you want me to make it a separate video?
Yes, that would be awesome.
I know, I
I
have to
would
figure
also
out
agree.
where it is, because there it is. Make it a separate one.